Hello class, and welcome to Chapter 5, which is all about piecewise functions. The first piecewise function that we are going to look at is absolute value functions, and this is Section 5.1. By the end of today's lesson, you will be able to analyze piecewise functions, including those that have absolute value expressions. So the absolute value function is y is equal to absolute value of x. Or you might see it written as f of x is equal to the absolute value of x in that function notation. To be perfectly honest, your book is much more prone to using the function notation, but I know a lot of you prefer y, so both of those options are out there. The vertex of an absolute value function is the pointed piece. So down here, right here at the bottom in this example graph, this 0, 0 is the vertex. It's where the first piece of the graph, which is going down, changes into the second piece of the graph that's going up. The reason we call these piecewise functions is because in order to get the graph to work, we need two separate parts, or maybe 3 or 4. In the case of absolute value, it's going to be one part going down and one part going up. The pieces are going to reflect each other across the axis of symmetry. So in this case, for this original function, my axis of symmetry is going to be x is equal to 0. It's that vertical line, all of the x values, all the different y values where the x coordinate is 0. So that's the line that splits the graph in half. The vertex is the point where it changes. So this is what we have for our absolute value function. Again, this is the general graph that would match this initial equation, f of x is equal to the absolute value of x. So, obviously that's not that fun if we're only looking at one equation, so let's talk about what happens if it changes. So we've got our original function, the absolute value of x. How is the domain and range different for the graph of negative 2 times the absolute value of x? So, domain being our x values, we're looking at the different things that we can plug in if we add multiplying by 2 in the front. If we go back and look at the domain of this original graph, I could plug in any x value. Looking at this new function that they give us, we can still plug in any x value. You can still take the absolute value of any number that you can come up with. So the domain of both functions is all real numbers. Any single number that you can think of to plug in, you are allowed to plug into this function. Now, let's look at the range. Initially, all of my y values were above the y-axis, or on it. So this lowest point here was 0. All of the other points were above the line. So the original range of this function was y is greater than or equal to 0. Now, if I come over here and I look, I'm going to figure out a few different outputs to help me decide what that range is. So if I plug in negative 2 for x, the absolute value of negative 2 is 2. 2 times negative 2 is negative 4. If I plug in negative 1, I've got absolute value of negative 1 is positive 1 times negative 2 is negative 2. Then I've got 0. Absolute value of 0 is 0 times negative 2 is still 0. Then I've got, if I plug in 1, absolute value is 1 times negative 2 is negative 2. And if I plug in 2, absolute value of 2 is 2 times negative 2 gives me negative 4. So looking at these range values, these y pieces, 0 is now my highest point. So the range changes with this one. So our domain, we can still plug in any number, but for the range, the absolute value of x is y is greater than or equal to 0, whereas negative 2 absolute value of x is y has to be less than or equal to 0. So the range changed with this one. Sometimes the range won't change, sometimes it will. You have to go ahead and plug in those numbers to figure that out. I would suggest choosing 2, 3, 4, definitely using some positive, some negative, to figure out the exact change of those range values. The domain is never going to change because we can always plug in any real number. Go ahead and find the domain and range difference of this one on your own. In this case, again, the domain is both all real numbers. We can always plug in anything for x. And in this case, there also is no difference in the range. No matter what we plug in, all of those values are still going to be at or above 0. Another thing we want to be able to do is interpret the meaning of these absolute value graphs. So in this particular example, Jay is traveling to visit a friend in a neighboring state. The graph for the equation, which is shown below, is the distance away from the state line in miles at t hours. Assume the graph shows the entire trip. How long is this entire trip? Or excuse me, how far is the entire trip? So if we're looking here, it's saying that the graph shows the distance from the state line. So this is saying miles away from the state line. So this first part, Jay is starting to drive, and he's currently 45 miles away from the state line. As he's driving, he's getting closer and closer to crossing from one state into another. This is 0 miles away from the state line. And then he keeps going until he finishes his trip. So this first part of the graph, he's getting closer to the state line, and it took him 45 miles to reach that state line, to reach that 0 point. Then after he crosses the state line, he's still driving, and he reached another 45 miles, giving us a total of 90 miles to get from his original location to the final destination. In this next problem, we've got a different scenario, but same type of question. We've got a new equation for the cyclist traveling towards the water station, and then again, traveling away from it after she passes it. So go ahead and find the entire distance of the race. In this case, we've got the 20 miles to get to the water station, and then after that, she travels 15 miles to complete the race, giving her a total of 35 miles. Last thing we're going to look at is how we can rewrite these functions if we need to. So notice with our original function that we talked about on that first slide, it looked roughly like this. And now we have this new function that's flipped over and has been moved around. So our job is going to be to figure out exactly how that has happened. So when I'm writing my new function, I'm going to start with f of x. And then to get it to flip over, we're going to have a negative. That's what flips it upside down. And then originally, we were going up by 1 every time. Now if I'm looking at this function, as I'm going over 1, I've got to go down 1, 2, 3, 4, 5 spaces. So instead of having just regular f of x equals absolute value of x, we've changed the slope of that function to be negative 5. So that original function, if we go back and look at our original f of x is equal to absolute value of x, that slope out front we could have put 1 because we're going up 1 and over 1. But now, as we flipped it over, we're going down 5 and over 1. So we're changing that slope value out front of the equation. Go ahead and try this one on your own. Again, this is changing that slope value. It didn't flip over this time, so it stays positive. And then to get to the new one, we went up 1 and over 3. So that slope changes to a 1/3. If you have questions about this or anything else from the lesson, please let me know when you get to class.